This lecture is on section 7.5, and we will talk about testing a hypothesis about a population standard deviation or variance, which are essentially the same test, as standard deviation is just the square root of the variance, and vice versa, this variance is just a square of the standard deviation. In this section, we want to adopt the hypothesis testing procedure that we've reviewed and practiced in the 7.1 through 7.4 to test a hypothesis concerning a population variance. This table contains the correct formulation of the hypothesis for a test of the variance. So if we see that we have a null hypothesis, we'll always have the equal sign. Recall that in stats 1, we used equal, greater than or equal to, and less than or equal to make it easier for us to see that the null and the alternative hypotheses had to be complements of each other. So for a two-tailed, you have a not equal to sign in the alternative. A right-tailed is a greater than sign and also looks like an arrow pointing to the right. And a left-tailed is a less than sign. First example, a pharmaceutical company believes that its manufacturing process is in control when the standard deviation of the dosage in each tablet is 0.1 milligrams. The quality assurance manager is willing to shut down the manufacturing process if there is overwhelming evidence that the process has excessive variation, which means that you're producing these pills and each tablet isn't remotely near 0.1 milligrams, which could be detrimental to somebody's, to their life, depending on what the drug is. Now, we want to use a alpha 0.01 to perform a test to determine whether there is an excessive variation or not. Step 1 is to determine the null and the alternative hypotheses. So the null is that the manufacture process does not have excessive variation, and the alternative is that the manufacturing process does have excessive variation. Since the issue, in this example is variation, the hypothesis can be stated in terms of the standard deviation or the variance. Most hypothesis tests concerning the variance will be one-sided since small variation is desirable, while too much variation is undesirable. Because we are interested in determining if there is evidence that the process has excessive variation, the test will be right-tailed. So we're saying that there's no excessive variation in null, which means that 0.1 is 0.1, equal sign. And the alternative states that it is excessively overdosed, meaning that we see an excessive variation in the pill being more than 0.1. Specifying the level of significance, it was set at 0.01. And we validate the assumptions of the hypothesis test, identify the appropriate test statistic, and compute its value. So the assumptions that we have to check off is that the data is obtained from a random sample of size n. And that was always the case, but we are getting now, that was always the case, I should say, in stats 1, where it was assumed that the data was collected randomly and not biasedly. But we didn't necessarily run through these assumptions, and it's important now as we get more advanced in statistics to understand the things that we need to understand about the data set in order to even know if we do any calculations on it, will it even be valid? And it would not be valid if the data was not collected properly. The second assumption is that the population is normally distributed with a mean and a standard deviation. Test statistic is going to be chi-squared, which can be calculated by n-1 times the sample standard deviation squared, which is the variance, over the population standard deviation squared, which is the variance of the population, with degrees of freedom n-1. Now, this, unfortunately, chi-squared is not in our guru for summary statistics. And what I mean by that is you can do a chi-squared test with a data set in our guru, but unfortunately, just having the standard deviation and alpha and all that is not, there is no screen in our Guru for that. So we will be doing this in Excel instead. So let me actually jump over. Well, you know what? Let's run through this one in the PowerPoint, and then I'll jump over to Excel to show you how to find those values. So calculating chi-squared, there is no cheat sheet. You literally just calculate this, but it's very straightforward. Okay, n is the sample size. Sigma naught is the claimed value of the population standard deviation, so that would be in the null and alternative. Sigma squared is the claimed variance. S is the sample standard deviation, and S squared is a sample variance. Note that the test statistic is named chi-squared. Be careful, do not mispronounce it as chi squared because of the way it's spelled. It's pronounced chi. Because that is the type of distribution the statistic has under repeated sampling, repeatedly calculating this statistic using different random samples from the same population. Let's look at the pieces of this new test statistic. The term, the population variance, sigma squared naught, refers to the hypothesized value of the variance. In this sample, sigma naught is 0.1, which implies that the variance is 0.01, because remember, the standard deviation is just a square root of variance. So to go from standard deviation, 0.1, to 0.01, the variance, you square it. 0.1 squared is 0.01. The actual variance of the population is unknown, but the sample variance, S squared, should be reasonably close to the unknown population variance. If the null hypothesis is true, then sigma squared is 0.01, and the ratio between S squared and sigma squared should be close to 1. Since S squared should be close to sigma squared, that's where we get the assumption that the fraction should be 1. Assuming the null hypothesis is true, multiplying this ratio by n minus 1 should produce a result near n minus 1. If the chi-squared expression is a great deal larger than the n minus 1, then S squared is a great deal larger than sigma squared. Such an event would cast doubt on the validity of the null hypothesis. Suppose the population is verified to be normally distributed. Also, suppose the random sample of 30 tablets are evaluated and the standard deviation is found to be 0.14 milligrams for those 30 tablets. The chi-squared test statistic is as follows. So we're going to calculate chi-squared by taking 30 minus 1, S squared, which is the variance, we would take 0.14 of the sample and square it, and divide it by the hypothesized variance, which is 0.1 squared. Our chi-squared statistic comes out to be 56.84. Now we need to determine the critical values. So when we were reviewing Chapter 7, we were focused heavily on p-values, but recall there is a critical value method where we are rejecting or fail to reject regions in the curve. So here's the chi-squared curve. Notice the chi-squared curve is a right-tailed curve, or it's essentially not symmetric, and it fits certain data values such as when we are testing the variance and standard deviation. So we have two-tailed, left-tailed, and right-tailed. In this case, we are doing a right-tailed test. We found the chi-squared statistic, but we need to mark the critical value between reject and fail to reject. So if the chi-squared statistic is larger than this critical value we need to find, then we'll be rejecting the null hypothesis and stating that there is excessive difference from tablet to tablet. And if the chi-squared statistic that we just calculated at 56.84 is smaller than the critical value, we will fail to reject the null hypothesis and therefore concluding that there is not a large variation from tablet to tablet. So in order to get this critical value, we would use Excel. Let's do that now. I'm going to sharing. I'm going to now share my Excel file. So it's as simple as doing equals, start typing chi, You're going to want to select the chi-inverse right, again, because we're doing a right-tailed test, and we are trying to find the critical value. It tells me to put the probability in, which the probability was alpha, and that was set at 0.01. And then it tells me to put in the degrees of freedom, which is the sample size 30 minus 1, giving us 29. And then I hit enter. So my critical value is 49.59 if I was to round. So we can see that that's the value here in the PowerPoint, the 49.59 or 588 is they rounded a little farther out. So now if we note that the chi-squared statistic 56 is to the right of 49, and therefore we are rejecting the null hypothesis and claiming that the variation is excessive. So there's overwhelming evidence that the process variation exceeds the desired level, which means that our expectation is that the amount of active ingredients in tablet to tablet varies too much for it to be safe. Let's do another example. A sporting goods manufacturer claims that the variance of the strength in a certain fishing line is 15.9. A random sample of 15 fishing line spools has a variance of 21.8. Using an alpha level of 0.05, is there enough evidence to reject the manufacturer's claim and assume the population is normally distributed? Okay, well, let's list our hypotheses first. So because the sample is random and the population is normally distributed, you can use a chi-squared test. The claim is that the variance is 15.9, so the null and the alternative are null is the variance is equal to 15.9, and in this case we're doing a two-tailed test because we only care if it's not the same, not equal to 15.9. The test is two-tailed with a significance level of 0.05, and we have degrees of freedom of 14, taking the sample size of 15 and subtracting 1. Now we want to calculate the critical values for the chi-squared test. There is a table that you can do this from, and that can be found in my Stat Lab under Tools for Success in the home screen. And then you look over for your tables. But remember, we can use Excel to calculate these values. So let's do that. We need to calculate a critical value for the left and a critical value for the right, since we have a two-tailed test. So in order to do that, we are going to, let's look at Excel. Hold on, let me stop sharing. And let's go into Excel. Okay, so you're going to do chi-inverse. That's for the left critical value. Now our alpha is 0.05, but it's two-tailed, so don't forget to divide by 2 when it's two-tailed with the degrees of freedom 14. So the critical value on the left side is 5.63. Now the critical value for the right side of the two-tailed test, we do equals, start typing chi, and we use inverse right. Again, it's 0.05 divided by 2 because it's a two-tailed test with the degrees of freedom of 14, giving me a right critical value of 26.11. So now we have our lower and upper critical values. We then need to calculate the chi-squared statistic so that we can see if the chi-squared statistic is smaller than our lower limit or larger than our upper limit. So here are the values we just found as our critical values. To calculate chi-squared, we take n minus 1, which is 14. Our sample variance is 21.8. And our population variance is 15.9. Notice there's no squares in this formula because before we knew standard deviation, so to get variance, we needed to square them. But in this particular example, we were given the variances and those are already good to go. Our chi-squared statistic is 19.195. And if we look at our upper limit, it's 26 and lower limit at 5, we are in between, and therefore we are going to fail to reject the null hypothesis. The figure shows the location of the rejection regions, bigger than 26, lower than 5.6. We see our chi-squared statistic falls in between in the safe zone, and we're failing to reject the null. So there is not enough evidence at the 5% level of significance to reject the claim that the variances of strength of the fishing line is 15.9. So essentially we're saying we do not have evidence to show that it's anything other than 15.9. And this concludes our lecture on 7.5.